Hello again, everyone. It's me, Joseph. Here's the Verilog portion of the Lab 7 presentation. So we're just going to get started with the iCache controller module. So if you see in your project folder, in the Verilog subsection, you'll have this file called iCache.sv, and here's a single module iCache. So remember, this is just the controller itself. So it has all of the signals that we were familiar with, right, where you have the imem to proc, right? So you're sort of putting this in between the processor and the memory, and then you have the proc to iCache signals as well and whatnot. And then also you'll have this uh, proc to imem that's going to go, or no, you have the iCache data and whatnot. Those are going to go to the actual cache. So if we open up the cache folder, we have this cache mem module, right? This is pretty much just the set of wires that you need to read the cache. So remember the logic, right? As we take our processor to iCache address, and we're going to use that to get a tag and an index. Using those, we're going to always store what the previous tag was, and we're going to detect if the tag changed based on the previous values not equaling the last values. And if they did change, that's going to determine whenever we're going to send a new value. And when we decide that the value missed, right, we're going to use the iCache valid or the cache invalid to determine if we got a hit or miss. Using those values, we'll combine those with this unanswered miss to determine if we need to send, if we have an outstanding miss, if we need to send a bustle read or no command at all to get the data into the cache, right? And then our default cases, right, we just got our negative ones, and just to say that as you initialize this, you have a new address. So if we look at the cache mem, right, we have all the same all of the same signals, right? Specifically these ones, right? The last index and current index, where we're going to have the ability to read an index and then also write an index, right? So we're going to also put in data to write and then put out data to read. We'll use our the output, which is going to be the last index and the last tag. That's going to decide which index we're going to use to read or write. All right, same thing with clock enable or clock and enable. Those are going to come from here if we're going to, for example, write. That will enable or write one enable. If you want to in your cache, right? Say for example, again, you have a superscalar processor. You may have more lanes for reading and writing, where maybe you can read and write to multiple cache blocks as long as they don't have the same address, for example. In here, right, we just have bit vectors for the data, the tags, and the valid bits. Right, it's 256 cache, remember, 256 byte cache. And so as we write data, we're going to write to the right index, whatever the data is, if the write enable is on. So I think this is fairly straightforward. Again, not as optimized as it could be, but again, should get the ball rolling. Also realize this is a set associative cache, right? It doesn't do anything. Not set. This is a direct map cache. There is no associativity implemented here. You'll probably, for instruction cache, that can work fine probably. You'll probably find it's better to get a set associative one for your data. So moving away from the cache on Bitbucket, right, we have a repository called memory example where we've written this memory test bench. This will show essentially just how the memory controller works. So again, we have a memory controller initialized with all of these wires where we have our clock, the proc to memory address, tags, responses, all of those, and they're declared as enums. And we have two tasks. So if you remember, the idea behind a task is that we have the ability to sort of do time sensitive or like delayed operations. So that's why we have pause edges of clocks and neg edge of clocks, and we can do delays inside this task. So this first task, write to memory, it's going to take in an address, our data, and the size, and then it will do the handshake that we were talking about, where we're going to put a command on the bus, and while the tag, right, the tag is always copied, right, after a positive clock, we're going to copy the tag as a mem2proc response. If the tag is not equal to 0, that means that we successfully sent our command, so we can continue and then just disable the bus command. With these mem busy get input, these are what we call semaphores, right? They're just a way to do locking. And so because the memory bus can only accept one request at a time, This is for synchronization, where we're going to synchronously, because we're going to call multiple of these functions at the same time. We're going to make sure that only one of the calls to either write memory or read memory can put a command on memory bus within the same clock cycle. So again, as we do the memory put, as we said before, the memory unit, when you send a write command, you can assume that the write essentially has happened once the tag or the response is non-zero, right? All reads to the same address will come back with whatever your new data is. I guess the other thing I'll add is this fork and join none. What this does is this makes this task non-blocking. So this task, when you call it, it does not actually wait for the transaction to finish. This fork and join none says essentially use a new thread to run all of this code and then just skip and end the task. So you do the same thing with read memory, where we have our tag. We're going to say acquire the lock and then put our command as bus load this time, whatever our size can be for the read. And this notice that for the read command, data is not an output. So when you supply this, you need to supply an actual variable for this function or task to copy the data to. I believe what I've done here is I just have this variable called temp where I never read the value. I just show that that's the data. I just put the data in there whenever it comes back. So everything else for the most part is the same, right? We put our command on, we wait till the positive clock, and we save our tag. If the tag says that we're not rejected, then we can proceed. And then this case, right, we're going to wait for the tag to not equal memory block. So notice here, we don't need a lock to get our data back, right? Multiple responses, for example, or multiple load commands can look at the same memory response or memory tag and get the same data. So we're going to keep waiting a positive clock until the tag equals memory to proc tag. In that case, we're going to save the data and then we'll just print our status to say that we got the data. Here are just two functions that will let us delay a certain number of clock periods. So if you want, I guess, a more textual explanation of what I've just gone over, that's here in this comment. But here is just our test case. So remember, all of these are non-blocking. So pretty much calling this read memory function will just create the request, but it does not actually wait for the request to get serviced or or even accepted. So what we've done here is we've created 3 requests, and then they're currently pending on the memory bus, or pending to be sent to memory bus, and then wait a positive clock. After one positive clock, these requests, one of them will get accepted, and then what we have next is we're going to send 4 more requests, right? Again, you'll see some of these addresses are the same. For example, this write memory to the read memory, right? You'll see that when we print out the output of this read memory, it's going to reflect the value that was set in this write memory. And then finally, we have this P clock, right? We're waiting 1,000 positive clocks. That's just going to make sure that all of the memory requests that are pending get satisfied. And then we're going to print our show memory decimal. So decimal, my bad. So let's turn on this define, or actually let's run it without the define, and I'll just show what this looks like. So we have a make file here, pretty simple. We're gonna make our simv, and then now we can run that. Oops, looks like my mouse is getting a little bit low. And so let's look at our output. So first thing we get a read of size word, right? So it's 4 bytes to address 20 times 15, right? So that's 32. And then you add this read, right? So first we're getting all of these reads. Here, I'll maximize this. So you see, we get all of these reads, and I believe the memory latency in cycles is set to, it should be set to 10, I believe. So it's going to take about 10 clock cycles for, excuse me, it's going to take about 10 clock cycles for all of these commands to finish. So all of these reads, you see we have 1, 2, 3, 4, 5 reads. If you look at our responses, we get 1, 2, 3, 4, 5 responses. So the first read we sent was to address 2, and then the memory has a default value of 0. So when this one responds later, right, it responds 100 nanoseconds later. So the read request was sent at 15, You see the response comes back at 115. So we're going to load 0 from that address. Same thing from 30, right? We're going to also load 0 from that address, right? 100 nanoseconds later, or 100 nanoseconds later. And then we're going to do a store to address 30. We're going to write the value 62 at time 135, and then we're going to read that address. And what you see is that, again, the stores, they don't get responses, right? They don't have to wait for the response to happen. But this load, which comes immediately after the store, right? Read to, or this one, which comes after this store, read to address 30 at time 55. When this one comes back, it gets the new value, right? And then we'll also see, right, we do another store to address 50, and then we have a read immediately after, it gets the correct value. So if you want to try and play around with the memory module, again, we're not going to require that you turn this in, but in this test bench, which you can try and do, is instantiate, right? You can add the icache.v.sv and the cachefm.sv and use these functions, right, along with the icache inputs and outputs from the controller. You can use these functions to simulate the reading and writing of memory values and then put them into the iCache, and you'll see like where you get hits and where you don't get hits. So yeah, and then you'll see at the end, actually here, I'll turn on the verbose mode and we can actually look more at what these signals will look like. So we can make SendV again. And so now what this is doing is we have a monitor on the commands, the addresses, responses, and tags. And then also if you want to open up DVE, you can see more of like what the timing looks like. Just another useful thing, if you have enums and you want to print out the enum value, or like the enumeration value as opposed to just like a bunch of numbers, you can dereference or use the dot operator to say dot name. That will convert the enum, that'll return a string that says what the state of the enum is, right? So you see I have a percent %s with a spacing of 9, and so I'm saying the enum name. So that's how we're getting this bus load and whatnot to print. So if we look when we start up for the first command, we're going to say, all right, hit a bus load. And then at the start, we're going to change the bus load wire or the processor command wire to bus load. We're going to change the address to 20. And then we have no response yet. Then at the negative edge of the clock, presumably sometime later, the processor is going to now give us a response of 1, right? And in that place, that's how we know that we can break out of, in the read memory, we can break out of this loop, and we're going to print this, right, read of size, whatever the size is, read of size word to this address, right? So that's kind of how this sequence is going. So the monitor is going to print, so the monitor that we added here is going to print the values as they change in here and in the memory unit. And then finally we can see how these tasks, once they get out of this loop, they'll print out what commands have they sent or what responses have they gotten. So we'll see the same things here as we send these reads and whatnot. We'll get the response, right? Once the command goes to bus none, you'll see that the process response goes back to 0. And then sometime later, right? So this is at time 75. Sometime later, we get the processor response to go, the processor tag to go to 1. That's how we can break out of this loop, this loop in the read response. When this tag comes out, this first read that was waiting on tag 1 knows that its data is ready. And so it's going to say, I've loaded my data successfully. And then it will write the data to the temp variable, wherever that is. So, and it's a little bit, I guess the output's not as messy when you turn off the verbose flag, but it will show you sort of what the timing looks like with these intermediate, or with these signals for the memory controller. So with this, I think you should have the starting blocks for how you can implement your memory subsystem. I'll try and post some other, I guess, recommended readings. There are some slides at universities that sort of go into, how would I make a non-blocking cache and other strategies for that. I'll try and post some of those on Piazza. Otherwise, also post on Piazza if you have any more questions. But yeah, this is the end for Lab 7. Thank you and stay safe.